Limited. So today's tutorial, we're going to talk about the collaborative advanced fault analysis, addressing some of the functional safety verification challenges from the recently published Accellera functional safety white paper. About us, in brief, Optima Design Automation is the next generation automotive functional safety tool provider. We are based out of Nazareth, Israel. And we have a portfolio of advanced solutions for the complex safety and security challenges, and a revolutionary high-performance fault analysis technology. So the basis of our technology is the Optima fault injection engine, which is orders of magnitude faster than the competing solutions. On the FIE technology, we have built Optima-HE, which is the static analysis solution. Optima-HE for hard error coverage to measure and boost the coverage for the hard errors, which are permanent faults. Optima-SE, which is the soft error or transient fault analysis. And we do have security solutions for IC security verification called Optima-SEC. And we provide safety related services as well in the design and verification of the ASICs. And we are funded by the European Union by the Horizon 2020 project. It's based on this tutorial. Tutorial is based on the recently published white paper, as I said, functional safety by Functional Safety Working Group. And what this talks about is that there are multiple tools that are possible and that are used to make sure that functional safety verification is done. And exchange of the data between these tools, right? Functional safety data. That's what it talks about. So the main point they touch about is that automation tools have been developed in parallel and currently lack a standard format or a language to exchange and integrate the data. And some of the things what they want to address is that unify and standardize a methodology to exchange functional safety data for FS operations like analysis, verification and validation, optimization, implementation, etc. So the focus of this tutorial is the FUSA verification by fault injection. And goals and future requirements as mentioned in Accellera white paper, I just mentioned. How Optima Design Automation addresses this challenge. The challenges meaning the intuitive fault classification, early and accurate feedback to the FMEDA, and multiple tool setup and data exchange. So what it takes, the ISO 26262 requirements are simplified in this slide, mentioning about the semiconductor chips, which need to have a safety mechanism. The safety mechanism is to detect or correct the faults within the budgeted time interval. And this safety mechanism needs to be running continuously while the device is operating. So it needs to have a safety mechanism which has a diagnostic coverage by quantitative analysis, not qualitative analysis anymore, by way of ISO 26262 recommendation. So to do the quantitative analysis and make sure that your SM safety mechanism needs to be able to cover nothing less than N%, and this N depends on what kind of ASIL level you are looking at. So for example, for ASIL D, you need this N to be 99%. So most of the 99% faults have to be covered by your safety mechanism. So what ISO 26262 part 11 defines is that for a safety concept with semiconductor components, fault injection is a known methodology for various safety lifecycle activities. What is this fault injection objectives as defined in the ISO 26262? Is to find the diagnostic coverage and fault tolerant time interval, fault reaction time interval, and architectural metrics like SPFM, LFM, and fit rate. The fault effects and the safety mechanism mitigation. In case if you are actually want to verify your safety mechanism and the correctness of the safety mechanism, not just diagnostic coverage, but the functionality of the safety mechanism, fault injection can be used. And so we just talked about the fault injections. What are these faults and different types? So ISO 26262 actually throws some light on the definitions of it. Safe fault, single point fault, residual fault, and multiple fault. So what is safe fault? A fault that will not violate the safety goal. So obviously, anything that doesn't violate our safety goal is safe. And single point fault, it violates the safety goal, but there is no safety mechanism present. So we all classify them as single point fault. So what is a residual fault? So the fault violates the safety goal, and there is a safety mechanism, but safety mechanism is not designed properly and is not covered by the designated safety mechanism. So that's what we call it as a residual fault. A multi-point fault, by definition, is like a combination of more than one fault that violates the safety goal. So ISO 26262 also defines various metrics for various ASIL levels. For example, at ASIL level A, these metrics doesn't matter. And at ASIL level D, the fit rate of 10, less than 10, SPFM of greater than 99%, and LFM of 90% is what is recommended. So Optima Safety Platform fault classification is very intuitive. We'll see in the next few slides, and very easy to handle, so that you can get started with the standard process, like whatever is recommended by ISO 26262, and start filling your FMEDA. So we know what are different kinds of faults and fault classification that ISO 26262 recommends. So it also recommends some kind of methodology to follow. So one of the first thing in the methodology is to define your failure modes. So what are failure modes? So this is defined as the manner in which an element fails in your design to provide the intended behavior. And failure mode is nothing but a set of signals violating the safety goal, which we call it as failure strobes, and signals that are used to detect the faults, which are detection strobes. These are usually from the safety mechanism. And also the list of faults that cause a failure. So in essence, the standard defines metrics calculated by injecting random faults and analyze the fault's behavior to assess effectiveness of the safety mechanisms for different failure modes. So here I'm just depicting failure strobes, detection strobes for your top level design and the DUT. And DUT is the one which you want to do the fault analysis. So what are the challenges in this fault analysis? So it's very complex setup. Multiple tools are supposed to be used. That's what the Accellera paper also is touching base on. And failure mode definitions using large and complex scripts. A number of faults to analyze is very large. As design grows, number of faults to analyze also grows. And the fault simulation with the current technology and the algorithms that are implemented, it's very slow and starts with a large fault list and end up simulating all of them. So there is no concept of only taking the relevant faults and moving ahead. And the fault classification, it's not at all intuitive, because every methodology follows their own definitions of what is the fault that is detectable, that is correctable, and things like that. So there is no standard definitions, as well as it's not intuitive, so that user can map into the FMEDA or ISO 26262 classification. And all the tools or methodologies handle soft and hard errors similarly. But to calculate some of the metrics like AVF, which is architectural vulnerability factor, which we'll see in the next few slides. So to be calculated, and SPFM for the soft errors should be calculated in a different way. And the turnaround time is very large, and interfaces to the standard FMEDA tools is complex and ad hoc. So these are some of the challenges which are brought out by different users and those who are doing the functional safety verification. So what Optima Safety Platform does is to solve some of these issues by integrating all the core engines, Optima-HE for static analysis, HE for hard error analysis, SE for soft error, and SEC as a security verification engine. So this all put together forms the Optima Safety Platform, and all the tools work in the single platform. So we are avoiding multiple tools and multiple setups, and we are actually addressing one of the major issues in the methodology currently. And we do have the Optima DB, Fault DB, and we provide a lot of visibility and the debug information with the faults and the way safety mechanism is defined. And the use model is simply depicted here by mentioning the RTL and GL is one of the inputs, and stimulus is another input, which is in the form of VCD, that we take it as workload or use case. And the safety setup, we'll know what safety setup is in the coming slide. But to define here, safety setup is nothing but defining your failure mode, right? So to the fault injection analysis. And we have a certain format to output to your FMEDA where you can just consume it, or consume from FMEDA, the safety setup it generates. So this is simply the use model and the integration of all the technologies in one platform. So this depicts the flow of the Optima safety platform for both hard and soft error analysis. So the initial setup is same, not like the other methodologies where you need to set up each tool separately, each formats are different and things like that. So you set up by loading the design, configuring the safety setup. So defining safety setup is nothing but the failure mode, and do the static analysis to identify what are the relevant faults. As I said, one of the issue is that you may end up analyzing all the faults and debug the fault result in such a way that what are the relevant faults and what are not relevant faults. Instead of that, we take the other approach where we decide upfront what are the relevant faults and then move ahead. So you can take one of these paths. If you are analyzing hard error, take this path. And if you're analyzing soft errors, take this path. But all this in the single platform. You set up once and then keep going. So here we have something called constant analysis. We do constant analysis, which is kind of a semi-formal approach, and move to the fault simulation for the hard error or the soft error simulations. And if you're doing hard error simulation, you go to the coverage maximizer, which actually look at the holes of your coverage, fault coverage, and tries to suggest some methods, right? So to go and fix the coverage holes. Or if you're doing software analysis, you go calculate the AVF and thereby the fit rate and the SPFM, and finally generate your FMEDA work products or the reports for further analysis. So this is, in brief, the whole setup and the flow we follow for both hard error and the soft error analysis. So what are the objectives when you get started with DUSA, right? So the first thing you want to find out is any non-safety critical areas in my design. So is my whole design is safety critical? Can I avoid some parts of the design and then analyze only the safety critical parts of my design? So this is the first question you start with. And also that what are the safety critical faults? If I have some safety critical blocks in my design, and are they violating the safety goal, which we call it as PVSG, potentially violating the safety goal? And what are the relevant faults for the analysis? How many are safe in them? And do all the PVSG faults have the safety mechanism in place? And that's what ends up in calculating our SPF, single point faults, which doesn't have a safety mechanism. Are there too many? Or can you sign them off that they don't require any safety mechanism? So these are the decisions you want to make. Or can the existing safety mechanism be used for detection of these single point faults, or do I need to design separately? This is another question you might be looking for an answer. How many faults are potentially detectable, and what is my DC, SPFM coverage to start building the FMEDA? So these are some of the objectives to start with, and Optima safety platform will solve one by one in the entire methodology and the flow we propose. And here we are going to talk about each engine separately in the Optima safety platform. And this is one safety platform, and in which you can do all of these things at one go. So now we talk about the static analysis in the next few slides. So the objectives of static analysis is basically objectives or requirements, right? So to run on RTL or gate level netlist. RTL because we want to identify the safety issues very early in the design cycle, and gate level is for the final result or the sign off for your fault analysis. And it should be simple enough and reusable for the entire DUSA verification. And no fault simulation at this stage because we want to do it fast and quick to get started with FMEDA as well. And one of the requirements also is the fault list management, where you can prune the faults, you can collapse them, optimize them so that you can run on some sample or exhaustive fault list. So to get started, how do we figure out the relevant faults, or how the relevant faults are important to figure out, right? So static analysis is based on the strobes which we define as a safety setup, as I mentioned. The failure strobe is the ones where the fault will violate the safety goal, and detection strobe is the one where one fault gets detected. Okay. And for safety critical DUT, do you want to simulate all of them? For example, here I have a top module, a DUT, and a safety mechanism here. So, and there are 10 faults I picked up at different various parts of the design, right? And if I just look at this, and DUT is your point of interest to do the fault analysis, and by defining detection and failure scopes, do I really need to analyze all of them, right? So look at this carefully. Only F1 and F2 needs to be analyzed because F10 is non-safety critical because I can consider them as safe. And F4 is not even violating the safety goal, right? So if F4 is there, is it really reaching your failure stroke? No, I don't need to do it, right? And F7, no. F8 is within the safety mechanism, but is it really violating your safety goal? No, so you don't need to violate. So if you analyze this way, the cone of influence analysis done by Optima static analysis will let you know that F1, F2 is only the relevant faults and rest of them doesn't do it. So other methodologies probably suggest you that inject all the faults in the whole hierarchy and start debugging why F10 is not detected, why F9 is not detected, things like that. But the Optima safety platform straight away gives you the relevant faults like F1 and F2 to be moving forward. And by defining the safety setup, it's natural to get into the intuitive fault classification, like what is described in this slide here. So safety setup is a simple way to capture safety-related information by way of failure strokes and detection strokes. So by using Optima, you don't need to define where exactly you need to inject faults because we do intelligent analysis and try to see that where to inject faults and which are relevant for the current DUT and safety analysis. So this is the way you define the failure strokes and detection stroke with a simple syntax. And just observe the various faults in different areas. For example, the fault X is mentioned as fault here, which is here in this part of the design is not actually reaching your failure stroke, not actually reaching your detection stroke as well. That means it is safe because it is not violating the safety goal. It is invisible because the safety mechanism doesn't detect. So SI fault, what we classify them as a safe fault. And SV, UI, and UV, the same definition is given. And next, I want to pick up UI faults, which with this fault reaches only failure stroke. That means this is violating the safety goal. And X in this area is not reaching detection. That means the fault in this area of the design will violate the safety goal, but there is no safety mechanism. So by definition of the standard ISO 26262, this is called SPF, single point fault, because this fault doesn't have safety mechanism, but it's violating safety goal. So you can map straight away UI into SPF. So this way, the intuitive classification is carried out by Optima static analysis engine. And next of interest is UV, which is both can be detected as well as it is violating the safety goal. So UV is the potentially detectable fault. So SV, as I mentioned, the fault is occurring in the safety mechanism. So unless there is another fault, this is not going to violate safety goal. So we mark them as a safe visible. And these are the faults which need to be considered for the multi-point faults, where in combination this can violate. But right now, for us, this is not of interest. So the Optima safety analysis will give you a clue about which are the important faults to be considered for the further analysis, which is UV and UI. And the first, what we propose is to make sure that all your faults will have safety mechanism, right? That's what you first attack the UI area and then go to the UV area and then next to the simulation and things like that. So this is a simple classification, as I mentioned in the previous slide, and this is the definition. The only relevant faults to be analyzed because UI doesn't have a safety mechanism. This forms an SPF category, and UV is the possible detect, and this gives you the diagnostic coverage. So this is possible diagnostic coverage, and you can get started with this diagnostic coverage with FMEDA as well. So this is the intuitive classification of what ISO definition. So please recollect that in few slides earlier, we have seen this fault definition, which is safe faults, single point faults, residual faults, and things like that. So this can be directly mappable to the classification what Optima has done. So UI simply goes into single point faults, And residual faults will get into UV because these are the faults which are both detectable and the violating safety goal. So unless you simulate it, you will not know if the safety mechanism is working properly for all the faults. So what we are going to do is go to the next level and try to simulate them, right? So detected is this, latent fault is SV. Fault is present, but it's not visible, right? So that's why we can mark this as latent fault. So the fault classification by Optima Safety Platform is very intuitive, and this is the way we are actually addressing some of the issues. One of the issues talked in the white paper. So what are the advantages of the static analysis? Very early static analysis and fault mode sizing. And this is the fastest way to find the minimum number of faults in each failure mode. And you can get to know what is single point faults and work on improving their diagnostics. So attack first UI and solve them, reduce them to 0 if possible. And potentially detectable faults that violate the safety goal. This is what is unsafe visible, and this will give you the diagnostic coverage. And safe faults that do not violate the safety goal. So one of the important takeaway from the safe faults is that if you have designed and you know that some parts only can be in this area, and by mistake, if some of the designers have put them into a safety critical area where it violates the safety goal, you will get to know by looking into the safe faults category. So the advantage is minimal setup, just few commands, and only one setup for both static analysis and fault simulation. So we're going to continue with the same setup, no more setting up the tool. And it's very intuitive with the built-in fault statuses. You don't define, right? So that's another issue talked about in the sense that each individual user might define the fault statuses differently according to their own organizational fitment. So that might not be possible for their customer to understand their classification. So in this way, we have built-in statuses which can be intuitively classified and mapped into the standard. And it's integrated with the FMEDA work products as well. So this is the flow which we discussed. So load the design, set up the safety setup, and run the Optima Safety platform with the static analysis. And once you have the result, you can export it to the tool. Or if you're not satisfied with that, so examine the UI area first, which is the unsafe invisible. Add the detection points or design a new safety mechanism, close this loop. Or we have an automated method where we call it as the coverage maximizer static. And this can automate and tell you that which are the points to be added for the detection and then close this loop. So both manual and automated is supported. And still we don't have any simulation up to this point. So what next? So we have done the static analysis, we have come up with relevant faults, and we also have come up with some basic statistics, basic metrics for the FMEDA. And what next, right? So can static analysis results be understood by the next step? So this is the generic issue if you are going to have a methodology for FUSA verification with different tools, right? And which format to produce the result, because one tool doesn't understand probably the other tool's format. Or the optimizations done at this stage still valid at the next step, because you have analyzed using some other tool or your own way, right? And the relevant faults are only this. But for the next stage, can you carry the same optimizations or you have to do it again? We don't know. So is the next step completely a new tool or set up all over again? So these are some of the issues OSP, which is Optima Safety Platform, addresses moving forward. So we talk about HE route first and then go to the soft error route. So till now we have done static analysis, and then now we are going to look at the hard error engine. So as mentioned, the same setup can be used till loading the design, defining the safety setup, and doing the static analysis. Literally, it is only these commands that are used till now, right? So safety setup, probably you might split this in terms of defining failure strobes and detection strobes, and the same setup is carried forward. So once the result is available, do I have to regenerate things and what some of the issues we talked about the previous slide? But Optima Safety Platform solves them in terms of seamless flow of FUSA data. So I have every optimization, every result that is carried out, every algorithm carried out here will be actually moving forward, be used, and the same data is worked on by the rest of the flow. So coverage maximizer is what we are not discussing in this tutorial. But what I would like to discuss is the constant analysis with one command you can do it, and the hard error fault simulation. And together, put together, we call it as the hard error analysis. And we do have the fastest simulator in the market currently. So what are the faults we have to take it to the hard error engine? So only relevant faults. I think that's one of the issues we're solving. So what are the relevant issues? As mentioned, that UI is being solved, that is the single point faults are being solved by coverage maximizer. And the relevant faults, safe faults are not relevant. And these are multi-point faults, it's not relevant at this stage. The only relevant faults are unsafe visible, which are potentially detectable. So faults after collapsing, we take it, and UV faults are which are proved by Optima-HE, we're going to take it. And fault list optimization also will be done further by Optima-CA. We'll talk about it next slide. And then faults analyzed by CA will be marked as blocked or masked. So what happens is here, it's a hybrid formal technology, and the trace based on the trace info. The goal one is to identify the faults that are blocked, like save fault simulation time and early identification. And goal two is to identify why are they blocked. Excuse me for the typo here. And these are possible because there are a lot of config registers, mode registers that are possible in your design, which disables some parts of the logic, right? So these are actually safe faults because they're not going to change their values. And probably the workload also did not exist for some of the nodes, which can cause the blockage. So these are unsafe faults. So intelligently, the constant analysis will go make it blocked safe, blocked unsafe, or masked safe and masked unsafe. This will help in terms of identifying and putting more details to the user to know about how the design is and how the faults will behave after the hard error simulation is done. So this is the fault simulation for hard error. You have already done the static analysis. Now what is the requirement is the VCD, which is the use case or the workload we call it as, and do the simulation. And once you do the simulation, I'll show the simulation snapshot in the next slide. But what I want to focus now here is after analysis, what you're going to do is you're going to get the UV fault as UV detected and UV undetected, which we call it as residual, right? So now, after this stage, you're going to further classify the faults into the detected and the residual faults, which are also important classification for your ISO 26262 recommendation or the FMEDA products. So after doing this, and along with the previously done static analysis, you can straight away map the whole fault classification of Optima safety platform into the complete flowchart as defined in the ISO 26262 standard. I'm not going to go through the whole flowchart, but just to let you know a couple of them, right? So the first you define the hardware element for a failure rate. Is it safety related? SI, right? Because it was intuitively done already that what are the safe faults. So green, I'll mark it. These are all SA faults. And then you go check if my fault is actually violating the safety goal. Say if yes, and if there is a safety mechanism present or not. Oh, there is no safety mechanism. Then obviously you put it into the UI. So that's what we said. If the fault is there, it's directly reaching the failure mode, failure stroke, and there is no safety mechanism because it's not reaching the detection. So X is already defined in this area as UI, and this is where UI goes. So like this, you can analyze, and it's a very easy and intuitive classification of faults that fits directly into the ISO 26262 flowchart. So what is the result analysis? Are configurations and mode registers considered a constant? Yes. So if yes, then the tool Optima-CA will actually make them block safe or mask safe. And these are the faults which you can get it. And we also have a concept called EOT, which is end of trace. So your fault is not classified in any of those, any of the previously defined or shown the classification. and the simulation ended. So we marked it as EOT, but we have some intelligent mechanism, algorithm that is working inside where we can know that this end of trace is going to be safe or not, right? Even if you consider the next use case or next workload, if we with one workload, you can actually mark it as safe or unsafe. And if it is unsafe, probably you might go and look at the workload or your design. But if it is EOT safe, we are pretty much sure that even if you use the next workload, we are pretty sure the fault will not propagate and violate the safety goal. So that's an intelligent algorithm which is working inside. And you can also get how many UVs are detected by safety mechanism. This is nothing but the diagnostic coverage. And how many are not detected, which is nothing but residual fault. And you can most accurately, you can calculate now the diagnostic coverage and SPFM at this stage. And how to improve is like our next stage where the dynamic coverage maximizer will help you to improve further coverage. And this is a snapshot of the Optima-HE engine. And here you can see we have various parameters that are listed in each column for each fault, like say fault type, and then what is the static analysis resolution, what is the CA constant analysis resolution, and is it propagated or detected? What are the times at which it is propagated? And we also give the signal at which it got detected as well, right? So here, if you see, some of the statistics or the metrics we calculated is the fault tolerant time and fault time interval, right? So this is very important, and we give you the sense of how fault is behaving when both propagation and detection occurs. And we do have advanced analysis where if it propagates, meaning if it is violating the safety goal, after which or after how many cycles you're actually detecting them, right? If you don't detect within 3 cycles, let's say that you are using a dual core lockstep design and 2 cycles delay is there and 1 cycle for giving the input. So total 3 cycles is what is required to detect a fault, but it would have already violated the safety goal. So that is the difference. Difference in this time is called that fault tolerant time, right? So we do give that input as well for the user to know if your detection and propagation mechanism is in sync or not, or the safety mechanism you have designed will ultimately help you or not. And you can see here some of the faults are actually propagated but not detected, and some of them are propagated and as well as detected. So this is actually, it's a DCLS, but there is no delays of clock, so both are working simultaneously. So you see the propagation and detection at the same time. And here it ends the Optima-HE and the hard error analysis. And you can stop here if you're not, if your design or if your ASIL level doesn't warrant for a soft error analysis. But ISO 26262 actually recommends to have a different SPFM for your transient fault analysis. So transient faults we refer to as the soft error analysis. So once you do the static analysis, we are taking a different route and then try to see how the soft error analysis will help us in coming up with SPFM for transient faults as well as AVF to further calculate the fit rates. So this is the definitions. I just want to highlight that ISO 26262 actually recommends to use soft error analysis or the transient faults to do further functional safety analysis. And these faults are called transient faults, and then you should have a dedicated target of SPFM for transient faults as well. And then how do you define these soft errors and the AVF, right? So here I have taken a representative design, and the architectural vulnerability factor is defined in the standard as the probability that a fault in a design structure will result in a visible error, right, for the final output function. So if you take this, I have taken a couple of faults like F1, F2, F3, F4. And if you see F1, it is reaching only failure stroke. So we have a status for the fault which reaches only failure stroke. And if I take F2, it is reaching only detection stroke. It's the same classification as previously. But what we are trying to do is injecting a bit flip on the flops only, rather than like hard error where everywhere the fault is injected, right? So AVF actually depends on the architecture and how your test vector, not test vector really, how your architecture is blocking some of the faults like what I have defined here. So for example, F1 is directly propagating to the failure strobe, and any fault that occurs in the F1 actually is going to violate safety goal, right? So it has high AVF. Whereas in F4, F4 is not reaching anywhere. That means it is disappearing. So if it is disappearing, means your architecture is in such a way, your architecture could be in such a way that there is a bit that is blocking it, or the fault which is bit flipped on this flop, it is disappearing in the next few cycles, right? So for that, the AVF will be 0, because whatever you do and whatever you bit flip or do whatever here, the fault is not going to violate the safety goal, and that's where we call them as AVF as 0. So if all the flops have to be replaced and made safety compliant, do you really require all the flops to be replaced, or do you have to replace only for the AVFs which are greater than some number? So that is the analysis which you need to do and try to figure out the AVF for each and every flop, and try to identify which flops are vulnerable and try to replace them or harden them, right? So that's exactly what Optima-HE is intended to do. And how do you lower the AVF? By changing the design to make soft errors disappear. Like say, for example, put the gates or put a TMR kind of a flop, or replace each flop with red hot flip-flops, hardened flip-flops. But do you want to do for whole set of flops in the design, or do you want to do it for a set of flops which AVF is high? So module level versus flop level TMR, I think this we all know, whoever is doing the FUSA designs, right? So only some flops are vulnerable, so why replace every flop, or why replace the whole module? So the first need to run the Optima safety analysis, and based on the AVF, implement TMR on only vulnerable flops. So if you try to implement without running and without finding out AVF, that means that you're increasing your flop count and hence the area and power. So what are the advantages for Optima-HE? Optimal and the simple safety setup, because we already done the static analysis and we're just going to do the SE analysis for the software analysis. And user can specify number of faults to be injected because each safety architect will have their own recommendations. And what we recommend is inject 50 to 100 flops, 100 faults on each flop and try to simulate. These faults are injected over the simulation window and try to see that the faults can propagate or not. And I mean, as you all know that the fault that is injected at the initial stages might not propagate, but fault injected at some windows can reach the failure strobe. So you need to make sure that the faults are injected across the simulation window and try to see that if they violate the safety goal or not. And we do have the fault placement time flexibility where user can define or we can do it automatically. So if it is default, it is done equal time windows, or you can place it at random places. Or user can specify what times user wants to put inject fault by way of flip fault or the constant fault. And we do have the fastest simulation engine, like for example, 24 million faults. And then we have clocking of, like say, 1 millisecond per fault kind of a timing, where you can reduce your turnaround time drastically. So once you find out AVF for these 24 million faults, and fit calculations can be done, or SPFM for the whole flop set can be calculated. So in summary, Optima Safety Platform is a single platform for all the FUSA challenges. And the fast simulation engine, we do have very fast simulation engines for both hard error and soft errors and more accurate analysis. To define individual core engines and their objectives is that Optima-HE, early identification of FUSA problems, works on the earliest RTL, no simulation here, and we can optimize the fault list and the guided maximization. A constant analysis will help you in further reduce by marking them as safe blocked or safe masked. And hard errors like measuring and maximizing the diagnostic coverage, and soft errors, Optima-HE is for soft errors measuring SE duration and AVF and to calculate the SPFM. And this is how we are trying to solve some of the issues which are discussed in the white paper recently published. And we are looking forward to solve most of the problems and give the accurate results with turnaround times, faster turnaround times. Thank you. And you can reach me on any questions in the email after this call, or we do have some time. I think, yeah, so we have 20 minutes of time. Please feel free to. Yeah, so the first question is, your solution works for RTL digital design. Do you support also mixed signal designs, analog design? No, we do support only digital designs as of now. But as we are working with more and more users, right, I think what they do is they are making this as the digital portions and the feedback coming from the analog portions, those signals as failure and detection strobes, and trying to maximize the things which they couldn't do with mixed signal or analog design. But to answer your questions, we support only digital right now. Yeah, you're welcome. Yeah, it's probably late in the evening. I'm not sure everybody's still active. Hope audio was good without any